Superposition for electric force, that's the subject of this video. We just covered the equation for electric force, how to find it, what it depends on. I'll throw this down. Recall that the equation for the electric force is K times the charge of one. Remember, we're using Q for charge. The charge of the other particle divided by how far away they are squared. And these are in absolute values. It's the magnitude of the charge that matters. And remember, the K constant here is 8.9 times 10 to the 9th. I didn't give you a unit last time, I'm sorry. Newton meter squared over Coulomb squared. How wrong of me not to give you a unit. That number must have been meaningless last video. Okay, so I want you to suppose that we have three particles. Let's go ahead and put them down. I've got this particle A, and it's a positive charge. And I've got this particle B over here, also a positive charge. And then finally I have over here particle C, and let's make it a negative charge. Why don't we? My question is, well, what's the net force on the middle charge, on B? What's the net force on B? Well, superposition means that I can just add up all of the individual parts and figure out the net effect. That's how it worked with waves. Two waves added up. We would add their displacements to figure out the overall displacement. Here, we're just going to say all of the forces will add up from each individual particle. So I want to figure out first, what's the force from A on B? What force is going to happen on B because of charge A? Well, I have two positive charges, so B is going to be repelled this way, and this is a force on B from A. I'll clarify that. It's just from A. That's all I'm looking at right now. But I also have a force from C over here. Let's use a different color for that. And what do I have here? Well, this is positive, this is negative, so the force must be that way, and it must be a smaller vector because the two are not as close as the ones over here. So let me label some more things. Let's label this R1, the distance from here to here, and this will be R2, the distance from C to B. Okay. So that orange line must be the force from C. So both of these forces are acting on particle B. I need to add them up in order to figure out the net force. So let's keep everything in variable form right now, and then we'll switch over and put in some actual quantitative values in a minute. So net force is, well, it's just going to be the F from A, and that's going to be, I'm going to call this direction positive and that direction negative. So F from A, and I'm also going to add, well, there's this force from C. Oh, from C. So two forces there. Okay, I could expand this because I know my electric force equation, and that's what I'm going to do. Let's stick in just black from here on out. So K, Q1 times Q2, well, my Q1 here is the QA. This is my second charge, QB, and it's separated by a distance R1, so that R1 is squared. I do the same thing for this force. except my two charges are here and here. So this is K times the charge on B times the charge on C all over R2 squared. And remember, these charges are in absolute values. It's the magnitude, not the actual positive or negative value that matters in our problem solving. Okay, and that is all equal to the net force on B. So if I wanted to, I could make this a quantitative problem, and I could say, well, maybe this is positive 25 microcoulombs. This is micro, which means 10 to the negative sixth. Maybe this is 4 centimeters. Maybe on B we have a charge of 10 microcoulombs, and over here we have negative 15 microcoulombs. And R2, let's say, is 6 centimeters. So plugging all of this in, F net, oh, this is going to be a lot. 8.9 times 10 to the 9th newtons meters squared over coulomb squared. I'm going to just drop the units for now and then add newtons at the very end. 25 times 10 to the negative 6, because it's 25, and to convert this over to regular coulombs, I have to do times 10 to the negative 6. I have to do the same thing for my 10 charge, all divided by R1 squared, which is 0.04. Oh man, I'm losing my voice. Alright, that takes care of that term. Now I'm doing the other term. 10 to the 9, this is K. My first Q, 10 times 10 to the negative 6. Here's my second Q, 15 times 10 to the negative 6, because it's a microcoulomb. R2, well, that's 6 centimeters, so 0.06 squared. All of that comes out to some value like 139,439 newtons. That is a heck of a large force. And that would be quite the magic on your calculator. But that is the general procedure for how to figure out the force on a particular particle or point in space. You just take all of the individual parts, figure out the force from those parts, and then add everything together. All right, see you next time.